So AP Physics 2, 2015, question number 2. This was the first year they had this format of test, and this question had a lot of problems, but I'm going to go through it. They've kind of simplified the way you answer these questions. So this one probably asked you to do too much in this 25 minutes, but I'm going to go through it and kind of give you some tips. It's actually a fairly simple circuit. And in part A, they're asking you to, there was a student that said, okay, you close the switch and then bulb 1 as numbered there. Hopefully you have the printout in front of you for the actual question as well. And it says, the student thinks that bulb 1 gets dimmer when you close the switch. But basically I'm making an argument that it gets brighter because you can see what my reasoning is here, or you can read it. When you close that switch, bulbs 2 and 3 are in parallel, so you identify that. And when you have two bulbs in parallel, numbers 2 and 3, and you add the second one that's in parallel before you have it, you just have 1 and 2 in series. But now 2 and 3 are in parallel. That decreases the overall resistance of this circuit, as I've stated. And once you decrease the overall resistance of a circuit, that increases the circuit current, and bulb 1 gets all the circuit current because it's in series with the combination of 2 and 3 that are in parallel. So after you close the switch, bulb 1 will get brighter because brightness depends, power and brightness are directly proportional, and when you get more current in bulb 1, it will get brighter, not dimmer. So I disagree with the student. So and here's where the problem really bogs down in this part 2, and if you do it all symbolically, and I started off doing it symbolically over here on the left, and this starts off pretty easy. You know, if you have the total voltage equals the total current times the total resistance, when you have just the two that are in series, the 10 and the 10, you don't have the bulb 3 yet. The current is the voltage over the resistance. The total resistance is the sum of the two. So symbolically, you have an R plus an R is 2R. So the current is indicated here, E, or the voltage, electromotive force divided by 2R, and power is I squared R, so I plug in this for I, square it, so symbolically, I think you get a point for this. And that's where it really bogs down, try to get the power number 2 symbolically. And I think this is an alternate method that would get you full credit. Just make up some numbers. They're all, say, it's easy to analyze if you just put the numbers in, and you can probably skip a lot of the work I have here, but you have a 10, 10, 10, and make this a 20, make it as simple as possible. So in case number 1, you can show that, you know, the total resistance is 20, the potential difference I picked is 20, so the current is 1 amp, and so the power would be 10 watts. So you could skip a couple of these steps. I would do it this way. If you get stuck, just, you know, pick some numbers and work it through, and I think you'll get all, if not most of the points. You'll probably get all of them. And in the second case, two in parallel give you a 5. So these two together are 5. So the circuit resistance here is 15. So 10 plus 5. So the total current now, I, or T means total, is now 1.33 amps. So the current goes up. So then the bulb number 1 is going to have more current now. So its power is going to be its current, 1.33 squared, times its resistance, 10, so it has now a power of 17.8 watts. So it goes from 10 to 17, so it gets brighter, but they want the actual percent or multiplier, so P2 over P1, 17.8 over 10, is therefore you manipulate this, you get power 2, which is power new. They want you to use power new, equals 1.78 power 1. So that's a way to, you know, it's not a hard circuit to analyze, but to do it all symbolically is really cumbersome, and they won't ask the question that way. They made this question way more difficult. That's before they really knew how to ask these questions in a more concise manner. But so if you stumbled on that one, take heart. They're more directly done on the most recent tests. So to finish off part A, you have to then how does the result of your derivation of part A, part 2, that we just did, relate to the explanation of part 1? Well, since the new power is greater than the old power, so the new power is 1.78 times power 1, and you should say that power is directly related to brightness, therefore, since this holds true, then bulb 1 is brighter because it has more power. Once again, you could make a lot of arguments here with numbers, but you have to use some, you know, words as well, quantitative, qualitative. But at some point you got to say you agree with the student. And before you close the switch, there's only two bulbs that are in series, so you might not even need the delta symbol here, but each bulb is going to have half. You could use a V here even if you wanted to. I wouldn't use a V. I've used because they're using an E for the voltage of the battery. So each bulb is going to be half the voltage. So say the battery is 20 volts. Each one has 10 volts. When you close it, as you saw in the previous step, okay, you can calculate that. Since the two 10s in parallel come together to be 5 ohms, and you still have the bulb 1 is 10 ohms, the 10 ohm bulb has twice the voltage. It's going to have 2/3 the voltage as the combination of the parallel. So it's going to get 2/3 of the voltage. The first bulb is going to have, say, 13.3 volts. It's going to have 2/3 of the 20, and then the parallel combination is going to have 1/3. So the parallel combination is 1/3 the voltage. Which we're looking at here. They're asking about what happens with bulb 2, because they said that the bulb 2 is going to get dimmer, which it does, because now it has less voltage. So, or you could go with the current. You could show your calculation and say, hey, okay, the current goes down because all the current that there is now splits between two bulbs. That might be the easier way to say this one. Focus on the current. You probably could get by with that. Just say, hey, the current splits before it goes into two bulbs, and now bulb 2 has less current than it had before. And then you could carry on for part B, double I, and do the calculations. You can refer back to, so if you did a calculation that you want to use, you don't need to redo the calculation, but just say, go back, tell them where you got to go. Go back to the calculation part AII. Tell them where to go and look for the answer, because then they have to go back there and look. And you could see from your previous calculation that in the first circuit, before you closed the switch, the current in bulb 1 and bulb 2 was 1 amp. And then you could do the calculation, all right, showing that, as I just stated, that the current splits. The current in that circuit and circuit 2 is 1.33 amps, but it splits between bulbs 2 and 3. Half the current goes to bulb 2, half the current goes to bulb 3. The overall current's 1.33. So now the current went down, therefore the brightness goes down in bulb 2. That's numerical confirmation of part BI. So part C here, I think, is the most similar to how they will ask questions today, because this one doesn't take a whole lot of calculation and substantiation, but the basic ideas, if you know the basic ideas, when you put a capacitor in place of bulb 3, and this is something we've gone over a few times, but it's something that's still maybe a little vague in your minds. When you put a capacitor in a circuit, all right, when you first turn the circuit on, okay, the capacitor is just like a wire at that very instant. It's like a short circuit. So I mentioned that in part CI, what happens to the bulb 1 immediately after you turn the switch on, and then after you wait a while. So there's two places you got to look at when you have a capacitor. When you have a capacitor, it's like putting in a wire for that short period of time, millisecond. All right. So no current will go through bulb 2. All the current will bypass bulb 2. Bulb 2 will not be on, and there'll be a lot of current in the circuit, because there'll only be one resistor, the 10 ohm resistor, by our calculation previously. So bulb 1 will be very bright. It's going to be a lot of current, and all the current goes through bulb 1. No current will go bulb 2, because all the current will go up to the capacitor. But once the capacitor starts charging, it starts blocking current. And after a little while, and usually for most capacitors it's less than a second, that's called the time constant. You don't need to know that. But then it becomes like an open circuit, like you just opened up a switch. Okay, it acts like a switch. So then it goes back to being basically like the very original circuit number 1, where you had the open switch, so that it's the same current through bulbs 1 and 2. They will both be equally bright. So bulb 1 will start bright, it will get dim. Bulb 2 will be off, dim, and then it will get brighter until they equal, because when all is said and done, when things equalize here over long periods of time, a capacitor acts like an open circuit. Its voltage is still going to be the same as the voltage of bulb 2. So you could calculate the charge on it using C equals Q over V. Its voltage will be the same as bulb 2. And in our case, after a long period of time, it will have, if in circuit 1, bulb 2 ended up with 10 volts, half of the 20 volts, so the capacitor would end up being 10 volts, a potential difference. And if you knew its capacitance, C, you could figure out how much charge is stored on there, and you could figure out the energy stored in there and so forth. So that's another typical type of question that they ask. So, like I say, I think maybe part 1 and part or part A and part C are more typical, but well, part A I, but part A double I and triple I are not going to be something like that's not going to be asked, I don't believe. But this right here is more typical, like I've said. So ponder that, and don't lose heart if you had trouble there in the middle. This was a difficult problem. The scores on this question, I'm sure, were very low that year. I didn't look at the final results, but it was a troublesome question, I'm sure.